Hello and welcome. This is the video lecture for Chapter 2 out of the Conceptual Physical Science book, 5th edition by Hewitt, and we'll have these videos for you every week. And Chapter 2 talks about Newton's laws of motion. Be sure to watch these videos before you do your homework and the reading every week. Let's get started. So in this lecture, we're going to help you understand Newton's 3 laws of motion, how they interact with forces, and the summary of the 3 laws. And this is very important stuff you need to memorize. So let's look at Newton's first law of motion. And I'll go through these as the PowerPoint does, and then I'll kind of put my own spin on how I word them. Newton's first law of motion is the law of inertia. Every object continues in a state of rest or of uniform speed in a straight line unless acted upon by a non-zero force. I would probably state it like this. An object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an outside force. So here are some examples of inertia. Why will the coin drop into the glass when a force accelerates the card? Or why does the downward motion and sudden stop of the hammer tighten the hammerhead? Inertia in action talks about the rapid deceleration sensed by a driver who lurches forward. It's also an example of Newton's second law, which we'll get to in a minute, because no force stops the driver while the brakes stop the vehicle. If you've ever ridden a bus or a metro train or subway, you know what this means. If you flip a coin in a high-speed airplane, it behaves as if the airplane were at rest. The coin keeps up with you. If there's a bird on a tree, can the bird drop down and catch the worm if the earth moves at 30 kilometers per second? How does that work? Well, let's look at Newton's second law of motion. And so the text says this: law of acceleration. The acceleration produced by a net force on an object is directly proportional to the net force in the same direction as the net force and is inversely proportional to the mass of the object. Well, what does that mean? Well, it's basically an equation. And the equation says this: force is equal to mass times acceleration. And you will see this as an equation on the next slide. It can also be rewritten as acceleration equaling the net force divided by mass. If you have a small force and a large mass, you have a small acceleration. If you have a large force and a small mass, you have a large acceleration. Now, in these equations, we talk about the letter small g, which is the force of gravity, and it's 9.8 meters per second squared, or we can kind of round it off to 10 meters per second squared. Acceleration is in free fall. If the only force acting on a falling object is gravity, and we neglect air resistance, then the object is in free fall. And like I said here, it does say that it accelerates towards Earth at 10 meters per second every second. So if we have twice the force on twice the mass, we'll have the same acceleration as half the force on half the mass. When the acceleration is in free fall, and you have a feather and a coin in a vacuum, so there's no air resistance here. In a vacuum, the feather and the coin will fall together at g, the rate of gravity and acceleration. Now, this was done as an experiment on the moon in the 1970s. When we went to the moon, we had a feather and a coin, or excuse me, a feather and a hammer, and they were dropped in the existence of a vacuum on the moon, and they both fell at the same rate. Of course, it doesn't happen on the Earth. The feather would have a lot more air resistance to it and would fall later on. So let's look at the situation. You have an air-filled gas tube. We've kind of looked at this already. Feather is going to fall with the coin. What happens? Will the feather hit the bottom first? Will the coin hit the bottom first? Both the coin and feather drop together side by side, or there is not enough information here to decide. What do you think? Take a look at this for a minute. Well, the answer is C. Both the coin and feather drop together side by side, as I mentioned before. Now, if we don't have a free-falling object and there is air resistance, then the air resistance is acting upward on the object, and the force due to gravity is acting downward. Let's look at this situation. Consider a heavy and a light person with the same size parachutes jumping together from the same altitude. Who will reach the ground first? The light person? The heavy person? Both at the same time, or there's not enough information? Look at that for a minute. What do you think? Well, the heavy person would, of course. They have a greater terminal velocity. Forces and interactions. A force is simply a push or a pull, and the interaction occurs between one thing and another. So when you push against a wall, that wall is going to push back against you. That's a force. And so here is Newton's third law of motion, the law of action and reaction. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So when you press your hand against a wall, the wall simultaneously presses your hand. The hand and wall press on each other with equal and opposite forces. And so one force is called the action force, the other force is called the reaction force. They are co-pairs of a single interaction. Neither force exists without the other, and they are equal in strength and opposite in direction, and they always act on different objects. So if the same force is applied to two objects of different masses, the greater mass object will have a small acceleration. The smaller mass object will have a large acceleration. So let's look at one more illustration here. Consider a high-speed bus colliding head-on with an innocent little bug. The force of impact splatters the unfortunate little bug all over the windshield. So consider this. Which is greater, the force on the bug or the force on the bus? What do you think? Well, they are both the same. Equal, opposite reaction. And that's it for chapter 2. Thank you for watching.